In this video, we have an electron that is 1 centimeter away from a 2 microcoulomb charge, and we're going to find the electric force, the electric field, the delta V, the change in voltage or the change in electric potential, moving it from 1 to 2 centimeters, and then how much work must be done to move the electron. So for the electric force, we have a negatively charged particle, which is our electron right over here, that starts 1 centimeter away from our 2 microcoulomb charge. And if we wanted to find the electric force, we would go ahead and use Coulomb's law with the constant K, and then we'll have a little q and a capital Q divided by the separation distance squared. And we'll call the um, capital Q the main charge that's producing the electric field, and then we'll have little q be the electron, the charge that's sitting in its field being affected by it. Now, with the electric force, it's just the amount of attraction between these two, so we're just going to find the amount of force in newtons between those two particles. But when we get to the electric field turns out to be a very similar formula, kq, capital Q, over r squared, and the capital Q being the 2 microcoulomb charge, because it's the amount of force per unit of charge. So how many newtons applied per coulomb of charge. So it's basically the same formula minus the charge of the thing that's sitting within the field. Now for the third one, for our voltage or electric potential, we have kq over r. And the reason why one more r is taken away from the denominator is because the electric potential is the amount of work done for pulling that particle from one point to another point. So with that being said, it's basically this electric field times a value of r, the distance it's pulled, and then it cancels out one of the r's in the denominator. Now, since all of these are very similar, they can easily be confused, but let's go ahead and plug in the numbers and see what we get for these different values, and then we'll go ahead and solve for the last couple portions of the problem. All right, now that we plugged in those numbers, we have a force of attraction of 2.88 times 10 to the negative 11th. I did not put the negative in for the charge of electron. I just took the magnitude of the charge. And then I'm just realizing that our electric field is this way, and our electric field is based on a positive test charge. So because we have a negative charge, it's going to go in the exact opposite direction. As I said, it was a force of attraction pulling in towards that positive particle. So this force is going inward towards that positively charged particle. For our electric field, that is the strength of this blue particle and how many newtons it applies per coulomb of charge, depending on what's sitting within its field. And then for our purple number here, we got 1.8 times 10 to the 6th volts. Volts is how many joules is required per coulomb of charge to pull it to that specific point. Our second one that we're going to solve for is we went from 1 centimeters to 2 centimeters. And as you notice, I put 0.01 because when we take 1 divided by 100, it's going to slide the decimal a couple places over to make it into meters. So if we do this voltage formula and plug in the 0.02 as opposed to the 0.01, which is exactly double of our separation distance, then that's going to split our second voltage in half. And then we're going to get 9 times 10 to the 5th volts. And then let's go ahead and mark these. This is for the 2 centimeter position, and then this one is for the 1 centimeter position. So the last thing we're going to do is we're going to go ahead and solve for how much work must be done to move that electron, and then we're going to find the work by doing work is the charge times the delta V. The charge for our electron is negative 1.6 times 10 to the negative 19th, and then our final voltage that is moved to is 9 times 10 to the fifth, subtracted by our initial voltage we were at, 1.8 times 10 to the sixth. And that leaves us with a value of 1.44 times 10 to the negative 13th joules. And it's a positive work value because if you think about it, the electron is naturally attracted to the positive force. So if you are pushing or pulling it against the direction that it naturally wants to move, then you are going to have to pump energy into that electron to push it away from that positively charged particle to give it more electric potential energy. So we have a work of 1.44 times 10 to the negative 13th joules. So between those four different things, the first three are very similar. Knowing the subtle differences between them, especially taking a look at the units, that can be very helpful in understanding each one of them. If you know it's newtons of force per coulomb of charge, joules of energy per coulomb of charge, and joules of energy used to transfer energy from one thing to another, that could definitely be very beneficial in understanding what you're solving for and what it's representing. So I hope that was helpful to you. Thank you for watching and listening.